Here we have a skydiver of mass 70 kilograms. As usual, the best way to start this is with a picture. The high diver is jumping off a board 10 meters above the water, and we're ignoring air resistance. If his downward motion is stopped 2 seconds after he enters the water, find the average upward force on him. So I see that this problem is going to be divided into two parts. The first one is the fall, and then the second one is the in the water. In this first part, we need to find out how fast is this diver going when they hit the water. That's something we care about. And then in the second part, we care about how long it takes them to stop and what force it takes to stop them. So let's figure out the fall first. I see the distance is 10 meters. If we draw a free body diagram for this diver, the diver is in free fall, so the only force is mg. This makes it very easy to figure out the acceleration. I know that F net is equal to ma, so ma equals mg. So this shows us that 70 kilograms, which is about 160 pounds, doesn't really matter at all in this. So a equals g equals 10 meters per second squared downward. We want to know the final speed. One way we could go about this is using this equation that a times the displacement, if I have a constant acceleration, is equal to v final squared minus v initial squared. This works for one-dimensional motion, which we have here, and we're assuming that the diver basically falls off the board so that the initial speed, v0, is equal to 0. So the acceleration is 10 meters per second squared, and the distance fallen, delta x here, is 10 meters, and that's going to equal v final squared minus 0 squared. So we have v final squared here, and I'm realizing that I wrote this equation incorrectly. I need a 2 here. 2a delta x is equal to v final squared minus v initial squared. So that says that 200 is equal to v final squared. I notice that I have correct dimensions here. Meters times meters is meters squared over seconds squared. Gives me the dimensions of velocity squared. So v final is going to equal, the square root of 200, which is the square root of 2 times the square root of 100, which is 10 times the square root of 2, or 14.1 meters per second is the speed of this diver upon hitting the surface of the water. That's pretty fast. V final of this part of the problem becomes our V initial for the second part of the problem. V initial equals 14 meters per second, and direction matters here. Direction is downward. Now we need a free body diagram for this new circumstance. I see that the diver doesn't suddenly lose mass, so there's still the weight acting downward, and there is the force of water acting upward. The net force then is force of water minus mg. mg in this case is 700 newtons, equals ma, 70 times a. Now what is a? A needs to be the change in velocity, so that's going to be v final minus v initial over how much time goes by. The motion is stopped after 2 seconds, so we see that we have two things we know. Time is 2 seconds, and v final is 0. I have 0 minus v initial, which is negative 14 meters per second if I take down to be negative, up to be positive. So this gives me an acceleration of 7 meters per second squared upward. So the force of the water minus 700 is equal to 70 kilograms times 7 meters per second squared. So the force of the water is equal to the weight of the diver, 700 newtons, plus 70 times 7 is 490 newtons. So this is 1,190 newtons is the upward force of the diver. Upward force of the water on the diver. This makes sense based on experience. When coming to a stop from a high speed during a dive, we do indeed feel more than our own weight accelerating or acting upward on us to bring us to a stop by accelerating us upward. Interestingly here, it's more than 50% more than the weight of the diver at rest in the air.